Okay, so let's welcome to the third session of Monday. We're going to hear Frederik's presentation about controlled natural languages. The floor is yours.
Yes, thank you. Let me screen share. Here we go. All right, yes, thank you. So just to briefly introduce myself, I just started doing a PhD in Germany on the topic of semantics extraction in STEM documents. I'm not really going to talk about that though, because well, I just started, so I don't have many results there. And what might also be relevant is that I'm a member of the Quark research group, which is led by my supervisor. And there we do a lot of knowledge representation and reasoning techniques and these kinds of things, with a particular focus on mathematical language and content and these kinds of things. Yeah, I already gave a talk in Stellenbosch at the GF Summer School at the last one, so 2.5 years ago or something. And there I had two different things I talked about. The main thing was that I had this idea of combining GF with a system called MMT, so that we get semantics. And then I talked a lot about mathematical language. And today I want to talk again about this idea of combining GF with MMT and what has happened since. So the system has a lot more matured. We've extended the idea. And therefore I focused a lot less on mathematical language today. But it will still come up though. Good. So as a background, when I talk about natural language semantics and these kinds of things, I basically talk about the problem that natural language is really messy and hard to work with for a computer. So we would like to get a nice semantic representation that's much easier to do inference with and so on. So basically logic is what I want. And so somehow we need to get from natural language to logic, and that's the problem I want to discuss. That has a long history. I want to talk about a particular approach, which is called method of fragments, which goes back already 50 years to Richard Montague. He was pioneering this idea a lot. And he basically said, so this problem is really hard, so let's make it easier by looking only at a small subset of natural language. So something like this. And you just take a small subset, which is nice, which is manageable. Maybe you can write a grammar for it or something, and you describe how that should be translated into logic. So you could, for example, have simple sentences like this, like Ahmed paints and Berta is quiet. And then you would say, well, the logical expression for that should, of course, be P of A. So P would be paint of Ahmed and Q of B, so quiet of Berta. So that's a small logic that we use here. Then you can get more ambitious. So you could just make a bigger fragment, cover more natural language. So here we have new words like every and nobody and so on, which also means that we need a more powerful logic, something like first order logic, maybe in this case. Good. So then you can keep getting more ambitious, making bigger things, or you could also look at a kind of specific phenomenon that's interesting. So here we talk about what things are allowed and not, and then we need again a specialized logic. So in this case, maybe a modal logic or something like that. And what I want to illustrate here, among other things, is that we really don't have one canonical logic. We kind of make logics up as we go. So we need a lot of flexibility there that will be relevant in a moment again. What I've been doing so far was hand waving how this translation works. I basically showed some sentences and said, obviously, it should look like that in logic. But in general, that's not obvious at all. So here's an example. If you say Ahmed paints, he is quiet, I could say, well, of course it means paint of Ahmed and quiet of Ahmed, except that in reality, dealing with pronouns and resolving them is not at all trivial, even though we intuitively can just do that, which means that we want to, which means that this hand waving is dangerous. We might miss a lot of the actual challenges involved if we just draw it like that. What Richard Montague did is he said you have to specify the whole translation. So basically 3 things. You have to specify a grammar and a target logic, and then a semantics construction. And the semantics construction would then translate from parse trees to logical expressions. And he wrote some papers where he illustrated, where he used this approach, and then you have lots of translation rules. So here's an example of that. The details are not relevant here. But our starting point was the claim that this doesn't really scale after some point anymore, because the rules get really complicated. And when you read a paper like that, it gets harder and harder to understand what's really happening and if it actually works or if there are some inconsistencies in there. And so as a consequence, we would like to do prototyping. That's our proposal. We want to make it easy to implement these things so that you don't have to do it on pen and paper. You can actually make a prototype, experiment with it, and see if it really works out, and show to other people, of course. Yeah, so this is the GF summer school. So of course, GF comes in because we need to deal with natural language. And it's very clear that we can use it at least for part of the problem. So we can use GF for parsing, we get our abstract syntax trees, and then we somehow need to get a bit further to reach logical expressions. And I want to show you 4 different ideas how we could continue from abstract syntax trees to logical expressions. And the 4th one is the one I'll talk about more afterwards. So the first idea is that we just use GF and we just treat logic like another language. So we make one concrete syntax for English and pass with that, and we make another concrete syntax for logic and linearize.
Sorry, excuse me. You have something blocking the view of the slide on the right side. Can you?
Really? Okay.
Or is it?
Ah, yes.
Yes.
Okay, that was invisible when I full screen. Interesting.
Yeah. Okay. Thanks. Now I see perfect.
Perfect. Yes. Yeah, I see that's relevant here. So the idea is we pass the sentence with the English concrete syntax and then linearize it with the logic concrete syntax, and we would nicely get a logical expression. And I'm sure everyone here knows how you would do that with GF. You just, instead of like the language and, you would just put the logical and so on. And I always use abbreviations. So instead of Ahmed in the logic, I just call things A and P for paint and so on. So this seems to work quite well for a simple example. But I make it a bit more interesting and say Ahmed is quiet and paints. So here we have a more complex verb phrase. And that becomes more difficult. So you can't easily do this with a concrete syntax because Ahmed, so A, has to go in several places. So it has to go in here, into the quiet and into the paint. And that's difficult to arrange. The standard trick is, which is also used by Richard Montague, to introduce lambda functions. So then you would get something like this. We translate the verb phrase to be quiet and paint. And we say, well, that's a lambda function. That's still, so you still need an argument, an x, and that is mapped to q of x and p of x. And then we could apply that here to a in this case, which means that if we simplify it and we plug in the a for x, we would get q of a and p of x. And yeah, you can again write a concrete syntax for that. And then you would have to use some external tool for doing the simplifications. That would be a first approach. I tried it a bit and I had some difficulties making sure I really get the expressions right, because if you just use strings for the logical expressions, then there's no type checking and these kinds of things. But maybe there's something smarter you can do. Another option, and I think that's also explained in the GF book, is that you make a second abstract syntax. So we have one abstract syntax for natural language, which we use for parsing. And then we have a second one for logic, in which we describe the logical expressions. And then somehow we map there. So in the abstract syntax, we would have 2 different categories, one for propositions, so for truth values, things that are true and false, and one for terms, like Ahmed, Berta, and so on. And then we can describe the operator. So for example, and would take 2 propositions, 2 truth values, and give us a new one. And Ahmed and Berta would be terms, and P and Q, so paint and quiet, they still need an argument, so they still need a term, and then we get a proposition from them. So what's left is somehow mapping from the abstract syntax for language to the logic abstract syntax. And there we can just make another abstract syntax for that, in which we define translation functions. So we might have a function here, TS, that takes a sentence and translates it to a proposition, because sentences are, in this idea, true or false, so we map them to the propositions. Similarly, we would map noun phrases to terms and verb phrases to predicates here. And then the nice thing is that we can actually define these translation functions. So we could, for example, here say the noun phrase Ahmed should be translated to A. And a sentence that was constructed with the and-s rule should be mapped to the logical and here we recursively apply the translation. And you can even use the lambdas that GF provides, which is very convenient. And then we can just use this approach, which means that we pass a sentence, we get the abstract syntax tree, and then we apply this translation with the put tree command and also the simplification, and we get a nice logical expression in the end. And if we wanted to, we could, of course, make another concrete syntax for the logic so that it prints things even nicer. Good. Then these were the first two approaches where we just use GF, another concrete syntax or another abstract syntax. Another option would be to just use a programming language, for example, Haskell. And well, you just give the abstract syntax trees to Haskell and do whatever you want with it, because it's, of course, a general purpose programming language, and somehow create logical expressions. And the fourth option would be to, instead of Haskell, use a more specialized tool for working with logic. And that's what I want to talk about. I have a specific framework in mind, which is called MMT. And then you can just hand the abstract syntax trees to MMT and do stuff there to create logical terms, logical expressions. So what is this MMT? MMT is a tool for doing logic development and knowledge representation. And it's developed by the research group I'm doing my PhD in, which of course means that we are heavily biased towards using it. And in a way, I was right now telling a story like we were looking for a logic tool for GF, but actually in a way, probably our thinking was more like we are looking for a language tool for MMT and found GF. Anyway, so in MMT, one of these ideas is that you can bring your own logic. So if you want to represent knowledge, write some ontology or something, you're not forced to use one specific logic that is implemented in MMT, but instead you can just take your own logic that you like and use it there. And then MMT provides all kinds of services, type checking and a module system and so on, independently of what logic you describe and use there. So bringing a logic means that you, most importantly, specify the syntax. And it's also possible to describe the semantics and maybe calculus or something, but that's less relevant for today. Because it's easy to implement logics, there is a project called Latin 2, where lots of logics are being implemented in MMT. So you have already a huge collection of a very modular graph of different logics that you could just use. Maybe what you need is already in there. Yeah, and it's really nice. So MMT and GF can be connected really nicely because MMT supports the type theory that's also underlying GF. So that makes this transition very intuitive. That means that we do three things with MMT. First, we take the abstract syntax and we just represent it in MMT so that we have it there. Then we declare a target logic. And then we declare a mapping, how to go from the abstract syntax to this target logic. So in the same way as we did it before as well with GF. Good. Yes, I have some examples here just to illustrate this. The first thing I said was represent the abstract syntax. And here you can see that they are really compatible. So on the left side here, you have GF, abstract syntax, and here we have the corresponding MMT content. And MMT, a module is called a theory. So we have your theory instead of abstract. And then for the syntactic categories here, we just introduce types. So S is a type, VP is a type, NP is a type. And then the functions would remain functions. We just use nicer errors, so Unicode errors here instead of ASCII errors. What's really useful is that the module structure is also compatible. So if you extend the grammar here, you can have a corresponding action in MMT, which is called an include, where you also just import everything from another theory. This is so straightforward that it's fully automated, and normally when you use this combined system, you wouldn't notice it anymore, and it would feel as if you work on the original abstract syntax, even though in the background it gets imported into MMT. Then you can declare target logic. And that's, again, the same way as I showed before in GF. So we would have a type for propositions. We usually use the letter O or Omicron for that. And then you could say not takes a proposition, so a truth value, and gives us a new one. A logical AND takes two values and gives us a new one, the same for the OR. And then we need another type for terms here. I'm showing you here a kind of simplified syntax. And I'll do that for the rest of the talk as well, but just for completeness. In real MMT syntax, it would look like this. There's a bit more going on, because you need to, for example, illustrate that this AND is an infix operator, and you need to set precedences and these kinds of things. That's just for completeness. And then the third step is we go from the abstract syntax to the logic. So from the grammar to the logic here. And we can describe that in MMT also in something which is called a view. And what we do here is we take all the symbols in the grammar and we map them to some expression in the logic. For example, we would say the syntactic category S would correspond to the type O, so to propositions. Noun phrases would correspond to terms, verb phrases to predicates. Then you could say, well, Ahmed corresponds to the term A, pain to the predicate P. And we can also define the functions using some lambdas. And with that, we can now pass a sentence. And then that's a new command, the construct command, which applies this substitution. And we get the logical expression. So technically, we would get a lot of lambda terms, but here it's simplified right now, which means we just get the desired Q of A and P of A. Good. So that's what I've shown you so far, just a high-level overview. We pass strings with GF. We apply this semantics construction, the translation to logical expressions in MMT. And the whole thing for usability has a Jupyter interface. I think you've all seen already the Jupyter notebooks for GF. This is based on that. So I won't talk much about it, but I briefly wanted to show it to you. So you can write texts in here, descriptions in Markdown. You can enter grammars like in the notebooks for GF. And here also the GF example. So I'll just scroll down a bit. You can also enter MMT content. That's the nice thing. So for example, here we have now this translation from the grammar to the logic. And the Jupyter kernel is very smart and knows that this is MMT content and knows what to do with it. And then we can just type commands here. For example, here we pass a sentence and we apply the semantics construction. And here in this case, I actively say, do not simplify the expression. That means we get all the lambdas still in here. So that's the square brackets. And otherwise, we would get the simplified expression if we don't do the simplification. Yeah, so that's how we normally use it in Jupyter notebooks, because that's easy. You have everything in one place. Otherwise, you need to open windows with MMT content, windows for GF code, and then another shell for doing the commands and so on. So here it's all in one place. Yeah, you see I left a bit of space here. That's because we've extended, that was the screenshot. That's because we've extended the idea a bit, and we added one more step afterwards and one more system. And that's the semantic pragmatic analysis. So the idea is that technically the semantics construction is not really powerful enough to do all things that we might want to do. So for example, if you want to eliminate ambiguities and these kinds of things, then you need an extra step that uses some inference to deal with ambiguities and all these things. So that means that in total, we now combine 3 frameworks: GF as a grammar framework, MMT as a logic framework, and this last one, which is called LP, as an inference framework. And together we get a new system, which is a natural language understanding framework. And we call it GLIF as an abbreviation for Grammatical Logical Inference Framework. So the plan is now that I briefly talk about LP and then just show you some examples what you can do with the whole thing. All right, so LP is an extension of Lambda Prolog, and Lambda Prolog is an extension of Prolog. And the most relevant thing here is that it has Lambda functions, which is really useful for our things. And the goal is that we use it as a kind of generic inference and reasoning step after we did the semantics construction with MMT. Let's take a look at an example here. For example, let's say we want to create a controlled natural language for describing physical properties. Maybe you want to ask physics problems, I don't know. So you would have sentences like the ball has a mass of 5 kilograms. And then we would use GF to write a grammar and parse it to get an abstract syntax tree. And we would use MMT to do a semantics construction and get a logical expression like this one here. This is not sure if it's the best way of doing it, but works for the example. The problem is that this can be ambiguous, which is of course not nice in a controlled natural language. So here's another example. Let's say something has a kinetic energy of 12 mn. Mn could stand for two different things here. It could either stand for millinewtons or for metanewtons. So we have probably two different abstract syntax trees that we get from GF, and then we get two different logical expressions. But of course, in a controlled natural language, we would prefer not to have this ambiguity. But if you think about it, millinewtons is a unit of force, which means it's not an energy. So actually, the first reading doesn't make any sense. And so in principle, we could just discard it. And then we are left with only one reading. So for that, we somehow have to check if the physical dimensions of the units and the quantities they describe, if they match up somehow. And that's where we could use LP. So the idea would be that we somehow implement this dimensional analysis in LP and use it for filtering the results. I'm not going to show you the LP code. It's not that interesting, but that's what it would look like in the notebook. So you would parse a sentence. That's more complicated. So here we have a ball with a mass of 5 kilograms and a kinetic energy of 12 mn. And then we apply the semantics construction. And that gives us two readings right now. One with millinewtons and one with metanewtons. But if we have described in LP another predicate for, so an LP predicate for that fails if there's a contradiction in the physical dimensions, and throw those things away, so that's this command here, then we are left with only one reading, only with the metanewton reading. Yeah, so that's an example. Here we use LP to just throw away readings that are contradictory. There's some other things you could do with it. And for that, I go back to math as an example. For example, we have here one short sentence, A, B, and C are pairwise disjoint. So maybe they're sets and they don't overlap. And this is an example from an actual controlled natural language called Forte that I was trying to re-implement a bit. The desired logical expression is A and B are disjoint, A and C are disjoint, and B and C are disjoint. And in this controlled natural language, it's always assumed that these relations are asymmetric, so we don't have to do the other direction. Good, so how do we implement that with this new framework? The first idea is that we could create the semantics construct. So we do parsing in GF, as you all would know how to do it. And then we would do the semantics construction in MMT. And there we would have to use lots of lambdas. That's getting quite tricky, but it kind of works. However, when I tried it at least, there were some artifacts. So you have these and T. So T here stands for true. And you have a bunch of those, just and true, because that was, otherwise it would have been even more difficult, I think, to do the semantics construction in MMT. So the challenge is that everything has to be typed, and that gets quite tricky. yeah, so we get these expressions, not exactly what we wanted, but now we could, of course, use LP and say we use it as a simplification step, and it just throws away everything we don't need and simplifies the expression until we get this one that we wanted. That's one way. So here we would use LP not for throwing away readings, but for simplifying the expressions. And another option would be that we say doing it with an MMT with all the lambdas gets too difficult. So we just create a preliminary expression. We don't go all the way to this expression. We just leave it at a preliminary state where we say, well, somehow you have to apply this disjoint relation to the list of A, B, C. And we leave it at that. And then LP could say, okay, I can expand this and actually turn it into the real logical expression, because that happens to work much easier with LP. And so with MMT, we would create an expression in a maybe more powerful logic that can be compiled down with LP. Maybe that's a way to think about it. That would be a second way. Good. So what these things were are different examples how we can use this pipeline. I'm going to call it the normal GLIF pipeline, where you pass, you do the semantics construction, and then you somehow improve, simplify, convert, adapt the logical expressions somehow using LP. However, when I was trying to come up with different examples, it turns out that it's quite tricky to find nice examples where you can use this semantic pragmatic analysis in this fashion. And instead, I came up with some examples where we just don't follow this pipeline and do something else with the framework instead. So I want to show you some examples of that. The first thing you could do, maybe for fun, is to use LP for question answering. So for, in this case, maybe for logic puzzles. So there I thought it might make sense to go to a more interesting logic, so not always just first order logic. And then you could ask logic puzzles. So here's, for example, John knows that Mary or Eve knows that Ping has a dog. Mary doesn't know if Ping has a dog. Does Eve know if Ping has a dog, as a question? And the goal is that we try to answer these questions automatically. And so we would use GF for parsing, and then MMT to translate to logic. So that's some form of epistemic logic. So here the idea is this box John would mean John knows that, and all the details are not that relevant. And we can also translate the question to a logical expression. And so we say this expression is true if and only if the answer to the question is yes. And then we can just use a theorem prover, maybe written in LP, to say, if we can prove the question from the previous sentences, so if you can logically follow that the answer has to be yes from the sentences, then we answer with yes. If we can refute it, if we can say, no, it definitely can't be the case, we say no. And what also happens very often is that we don't have enough information for an answer, and then we say maybe. And so if you run this, if you implement this, then you would get something like this. The commands get very long because I implemented that in a slightly older version where you couldn't enter multiple strings. So it all had to be in one long sentence in a way. Yeah, and so you would pass it, you apply the semantics construction, then some extra command to run the theorem prover. And so in this example, John knows that Mary has a dog. Does Mary have a dog? In this case, the theorem prover says, yes, that follows. And the other way around, if you say Mary has a dog, does John know that Mary has a dog? Then the answer is maybe. We can't answer that. So that's maybe just a fun example you can do. Another example, here we come back to what GF is kind of intended for, and we do translation. So we have an English sentence here. Kim is Ahmed's cousin and the father of Grace. And now let's say we want to translate that into German. The challenge is that there are two different words for cousin in German, one for a male cousin and one for a female cousin. So the same way there's one word for a male sibling, which is brother, and one for a female one, which is sister. They sound very similar. You could maybe say one is a feminine, one the masculine form, but then the example doesn't quite work as nicely anymore. So the way I implemented this is that in GF, I had two entries, one for female cousin and one for male cousin. And then if you pass that, you get two different abstract syntax trees, one with female cousin, one with male cousin, because it's the same word in English. And then when you linearize it, you get two different German translations. That's normal GF. And now the idea is that we could use this GLIF setup to discard one of the readings, because we know that Kim is the father of Grace. So Kim has to be male and can't be a female cousin at the same time in this model. So for that, we would do a semantics construction. And in this case, maybe not a complete one, because we don't care about all the information. And so we just have a partial semantics construction where we only look at the gender of people that we know about. So we would say here, in this reading, it's a female cousin. So Kim has to be female. And of course, Kim is a father. So Kim also has to be male. And in the other reading, it's a male cousin and a male parent, a father. And so, of course, you might argue that here that's a contradiction. Kim can't be both female and male, so we discard this reading, and we are left with only one translation. Yeah, so we can do that again with GLIF. I just showed a screenshot of the end of the notebook. Here, the idea is we pass the sentence, we do a semantics construction, and then we filter with the LP predicate check to throw away contradictory readings, and then we linearize with German. And GLIF is smart enough to know that we want to linearize the abstract syntax tree, of course, and not the logical expression that was generated from it. And without that, we would have gotten two different translations. Good. I'm gonna not go much into this. The idea is, right, that for that, of course, we have to implement something that finds contradictions and so on. And that can be a lot of work. And the idea was that we want to do easy prototyping with GLIF. So we want to make that as easy as possible. And it turns out that you can actually generate the prover automatically. The underlying idea is that you can describe inference rules in MMT. So for example, things like if you have a proof of A and B, then you get a proof of A. Or if you have a proof that X is male and you have a proof that X is female, then you get a contradiction. So you can write these things down. That's a well-known way of using logical frameworks. But from these things, you can directly generate a prolog or LP code where you basically say, well, if I want to prove, for example, a contradiction, then I just prove that some X is male and that X is also female. This doesn't quite run. It would right away diverge, but with some extra tricks, you can just guide the proof search a bit and get a very inefficient but working prover. And for these kinds of examples, it's perfectly sufficient. That means that really all the LP code you have to implement is this little bit here. So up here, we call some commands for generating the prover. And here we would import a couple of things and write one predicate, which basically tries to prove a contradiction based given this logical expression. And that's all. So that makes the prototyping maybe a bit easier, though I'm not sure for how many different logics this would really work. So one more example, because I always have a math background and I really like it, is I thought maybe we can create something like Wolfram Alpha. I think you know it, where you ask questions in English and get an answer for a math problem. And as a system, I looked at the computer algebra system SageMath for no particular reason. And so in SageMath, you can do commands like you say, G is the alternating group of 5, and then you could say what's G dot cardinality, and so on. And the idea is we could now try to ask, ask these things in English. So we say, let G be the alternating group on 5 symbols. What is the cardinality of G? And then to do that in GLIF, we would have a slightly different pipeline again. We would start with parsing in GF. We would do the semantics construction, but we don't go to logic. We go to another abstract syntax for Sage. And then we could have a linearization, so a concrete syntax where we get the Sage commands nicely printed out. And you could make this more complex. So you can support, of course, more input languages, maybe more different computer algebra systems as an output. And theoretically, but it's not necessary for this example, you could even have an intermediate representation in here where you do inference to figure things out from context, maybe pronoun resolution and so on. So this is just a minimal setup, but it works already quite nicely. And then you can, so I implemented a prototype that was actually a nice proof of concept because this prototype took only a few hours to make. So would have taken me a lot more probably if I had just started from scratch in a programming language. And you can ask questions like, let G be an alternating group on 5 symbols, and you get the command. And then you can also, so then you can start thinking, what other kinds of sentences could we support? And you can just try things out and say, maybe we could introduce notations. So we could introduce a notation bar H bar as a cardinality for getting the cardinality of something. And then maybe this corresponds to a function. So Sage is Python based, which means that this is a Python function simply. And then you can play around with these things and see what happens and where the limitations are before maybe you would say that you want to implement this large scale, and you can just try things out with GLIF quite easily. Yeah, so those were non-standard uses of the GLIF pipeline. I have one last example, which I put in the end because it's maybe a bit more complex, where we actually use this normal pipeline and use AP again to really just improve the semantic representation. And there I basically looked at an old paper of my supervisor from almost 20 years ago, where he proposed to use a model called Tableau machine to implement what's happening when a human reads a text. The idea was that if you read an ambiguous sentence, maybe you have the word she in there, then she could, of course, refer to many different people. But as a human, you wouldn't keep all those different possibilities in your mind and then get exponentially many things or models in your head. Instead, you would just pick the most likely one, the most natural one, and go with it. Unless, of course, you find a contradiction later on, then you would backtrack and update your belief. So I have here a very small and artificial example, and afterwards a slightly more interesting one. The idea here is that we have the sentence Ahmed or Bertha paints, so P of A or P of B. And there are two ways this could be true. Either Ahmed paints or Bertha paints. Those are the two possible things we could take from that. So if you know Tableau proofs, this is basically like that, just that you don't negate the formula. And so the idea is now as a human, you just pick one of the readings and go with it. That's the model that they proposed there. In this case, it would be P of A. And so you say, let's assume that Ahmed paints. And if now the next sentence is Ahmed doesn't paint, then of course you would say, well, now that doesn't make sense anymore. There's a contradiction. Probably my assumption was wrong. And you backtrack and say, well, then Bertha must paint. And you go with that model. That's the very small, example. I have one more interesting, maybe slightly less artificial one. Here we have here I want to do pronouns. So we need to know what things are masculine and feminine. And we have some word knowledge in the background here. So we would say John is masculine, Mary is feminine. And if someone is something or some word is feminine, then it's not masculine. And then we start reading sentences. So the first one is John talks to Mary. That's easy. We just add the knowledge to our model. We would say Sasha is sad. We just add it again. And now comes the interesting sentence. He loves her. That means we now have he and her. And so the logical expression would be something like there's an X that is masculine and there's a Y that is feminine, and X loves Y. And now we have to figure out who are X and Y, who are he and she. And as a heuristic, we could say, well, probably the most recently mentioned people. And so we start guessing maybe it was Sasha, right? So we would say, well, Sasha loves Sasha. So X and Y is both Sasha. That means that Sasha is masculine because we used he, and Sasha is feminine because we used her. And then according to our background knowledge, that's a contradiction. So that didn't work. Maybe we should try something else. And then you would say, well, maybe Sasha loves Mary. That means that Sasha is masculine. So we didn't know what gender Sasha has before. And we go with that. But now we could again just say we break the model. We say, well, actually Sasha's a woman, so he can't refer to Sasha. And so we again backtrack and we say, well, maybe Sasha loves John. That doesn't work out either. Maybe John loves Sasha, and so on. And you could keep playing this game. Yeah, so that was just one of the examples. And the idea here is that you can, or the hope is, what I want to advertise is that you can use GLIF to just implement these things and try them out. So here's some theoretical idea how humans read texts basically, and somebody might implement that on a logic level. But if we attach GF and maybe MMT, we get this translation from language to logic, so to the input of this model, so very easily. And we can, instead of just prototyping the pure logic thing, we can really do an implementation with natural language input to try it out entirely. Yeah. So here's a summary of all the things that we do when we specify this pipeline in GLIF. We would start with parsing, where we have a concrete and an abstract syntax to go from strings to abstract syntax trees. The abstract syntax is imported into MMT. And in MMT, we also describe the logic, maybe calculus, and here maybe some domain-specific things, and the semantic construction for the translation. That gives us some preliminary logical expressions. And then we use the semantic pragmatic analysis and LP to somehow improve them, refine them to get the final semantic representation, a model or just fewer readings or something like that. And for that, we might use the prover, which could be generated. I briefly sketched that. And we might also use world knowledge that might have been specified in MMT. Yeah, and the whole framework we call GLIF. So as a conclusion, I was kind of showing the idea that we have a framework GLIF, which combines 3 different frameworks, including GF, to do natural language understanding. And we often sell it for prototyping, as a prototyping idea, also because that makes it a bit easier to convince machine learning people who are very skeptical if you try symbolic things. Yeah, the access is via Jupyter notebooks. That because you have everything in one place, you can see it there. You can use it without Jupyter, but most people, I think, prefer using Jupyter. I say most people because we started using it for teaching natural language semantics lecture, and there we increasingly started using GLIF. So we started a few years ago, mostly with GF, and then GLIF gradually grew along with the lecture. Yeah. One drawback that I maybe should still mention is we use MMT because you can do so many different logics easily in there. But one drawback at the moment still is that you can't use discourse representation theory properly. So that's a very common logic used for natural language semantics. And we kind of did a bit of prototyping and it works a little bit, but it's not very usable yet. And it definitely is not good enough. So that's one of the major drawbacks that we have here. Yeah, I think that's all from me. Thank you very much, everyone, for listening. Do you have any questions?
Thank you. For questions, just speak up or raise hand if there are several people. Go ahead.
Thanks for the talk. So when I look at your pipeline, it reminds me a lot of what I know that some people were working on called Fragments.
Yes.
Which, you know about Fragments?
A bit, not too much. So I'm probably going to get something wrong, but I've heard of it.
Yeah, so basically what they do is they use GF, then translate GF to Coq expressions. So they have the type system and theory improving capabilities of Coq, but they also have a semantic pragmatic tool, I think implemented in Haskell to solve some problems. So what I was mostly wondering about was, so you showed some of the inference examples.
Yes.
But if you ever considered looking at how much you could cover of the Fracas test suite, which is particularly a test suite for that kind of inference?
I haven't looked into that really. I would love to, but I haven't done it yet. I think I might either do it myself, or maybe we would give that as another student topic to someone. I think
because I think that would be great to compare to other systems. So there are a few papers about FRACOG where they compare their systems against other systems. And that would probably be also a good starting point for your contribution to it.
Yes, that sounds very good. I think for FRACOG they already have parse trees, right? So you don't need to create a grammar anymore. Yeah, that's a good idea. We should emphasize try to push for that a bit more to try that out properly.
Thanks. Arne, next.
Yeah, thanks, Fredrik. A very clear presentation and a nice system. So I wonder if you have tried it in the order of generation from logical form to natural language. Because,
no, yes.
Yeah, that might be useful, for instance, if you are doing question answering and you want to answer in natural language.
Yes, we have not looked into that at all. Do you think that's easy from this system to go the other direction?
Yeah, I think it would be, so it would kind of complete it in some way, but that was just a little idea.
So my concern is always that inverting this step, the semantics construction, seems difficult if you want to go that way. If you want to get natural language sentences, because of course the logic tends to be less expressive than the language. So if you have something like this one here, where you have is quiet and pains, then you would have a duplication of Ahmed. And if you want to go back, then you would get already Ahmed is quiet and Ahmed pains.
Yes, then you have to do something for that step. But basically, since you have the same grammar for the questions and the answers, or at least they are related, so maybe that's nothing that you feel the need of. But I was just wondering that it might be a low-hanging thing.
Yeah, no, I'm really interested in that. I was always a bit scared of it, I think, but I think that's a good idea to look into, and I think a bit more about that. Thank you. Thanks. So I'll just show something like this again, because I think it's better. Yeah.
I could maybe continue a bit about that, because you had this first approach, which is to have a linearization to a logic. And I would just mention that we have used it in digital grammars for an industrial use case for the Z specification language, which is quite large, and it was used mainly in the generation purpose. And I think I was surprised how well it scaled up to do that.
Oh, that's great.
But it was we didn't use it or try it in the parsing direction, but more like in the generation direction. But having concrete syntax for logic worked in that case quite well.
Yes. That sounds interesting. You should try that. Yeah. Thank you. Yeah, I'm thinking about that right now. So.
If no one else has questions, I also have a question about what the issue was with DRT, because I wouldn't expect that to be so difficult. Was it? Yeah.
So so partly because probably we haven't spent a lot of time on that yet, but ultimately expressing it because MMT is a lot is very geared towards type theory, so things like LF and so on, and so DRT intentionally goes against the scoping of identifiers. Yes. Right, we can access something from outside its scope in a way. And if we want to do that in LF, then usually you have a binder and then the scope is more restricted. And that caused some problems. So there's a variant of DRT, which is called lambda DRT, I think. And we managed to implement that. So there we have, I think, typing and so, but I'm not sure quite what the status of that is. Actually, I didn't look much into that. Michael Kohlhase looked more into that. We don't think it's impossible, but it doesn't work out of the box easily.
Yeah, no, that's what I would expect also. And it can, or although you can already, I think you have a very nice way of resolving pronouns with inference. That's something that I wonder if DRT really has.
That's what Michael always says. We don't need DRT anymore because we could do something like this.
Any more questions, or shall we take a 10-minute break before Arne's talk?
Fine for me.
Okay.
Yeah,
so we'll resume Arne's talk 9:03 Singapore time, whatever that is your time zone. So we'll stop this recording.